This is my introductory video to derivatives, and a derivative is basically the instantaneous rate of change. And the notation for derivatives, there's two types of notation. It's f dash, you would read this f dash of x or f prime of x. I know I've made videos on like integration, I've used derivatives and stuff before, but let's just pretend that didn't happen. And I'm now making videos on how to take derivatives. So I'm going to explain. So yeah, you've got Newtonian notation, that's f dash of x, or you can use Leibniz notation, which is way cooler. If you see someone using Newtonian notation, I invite you to just stop being their friend, because they are what's ruining math. That's like saying anti-differentiation instead of integration, you know? Like, you just don't hang out with those kinds of kids, alright? Now, we've got dy dx. This is the way cooler notation, which makes way more sense. And if you get used to this notation, when you're doing stuff like related rates, it makes them so much easier. Dude, related rates are almost impossible with this notation. At least with this one, you can sort of like make stuff cancel each other out and, you know, manipulate algebraically. It's cool, man, it's cool. And this is like, one dash is representing the first derivative, two dashes represents the second derivative of the original function. Dy dx is the first derivative, and d squared y over dx squared is the second derivative. So the second derivative of y with respect to x, that's how you would read it. So the derivative of y with respect to x, that's way better. Anyway, what better way to learn how to do derivatives than to actually do some examples? Now there's 4 rules: the power rule, the chain rule, the product rule, and the quotient rule. Rule this, rule that, paddywhack, crack-a-lack. So I'm going to demonstrate a really easy example. So what we do when we're saying we're taking the derivative is we use shorthand notation, and this is what you call the derivative operator. So let's just say that y is equal to, I don't know, x cubed plus 2x plus 1. So when we're taking let's say we're taking the derivative with respect to x of y, and this is the same as dy dx, but I'm just making it abundantly clear that I'm using the derivative operator to find out the derivative of y. And that's equal to, well, if my function is x cubed plus 2x plus 1, here's how you do it. There's this thing called the power rule. In this example, we only use the power rule because the power rule is, you know how we say like x to the power of 3? That's where it gets its name from. Well, at least I think so. So if you've got an exponent of 3, what you do when you're doing differentiation by power rule is you pull that power out the front. So we've got x cubed, yeah, right here. So now it becomes 3 times x, but not x cubed, it's x cubed minus 1. So 3 minus 1, well, that's 2. So basically the idea is you drop off one value of the power and you bring the original power out the front. Alright, so we're taking the derivative of the first term. Fantastic. Now let's take the derivative of the second term, 2x. Well, that's the same as saying 2 to the x to the power of 1. So that's 1. That 1 comes out to the front, and that's 1 times 2. Well, that's just 2, right? So, and then that's x to the 1 minus 1. Because remember, you drop off one value of the power of the exponent, just like we did here. And that's x to the power of 0. Well, anything to the power of 0 is 1, right? So when we say that we're taking the derivative of 2x, that just becomes plus 2, yeah? And 1 is the same as saying 1 times x to the power of 0. And that's x to the power of 0 is effectively 1, yeah? So that doesn't change anything. But if we bring this, we're taking the derivative of this, we bring the 0 out the front, and that's 0 times 1, and that's 0, yeah? And then this is 0 to the 0 minus 1, but it doesn't make sense because it doesn't become 1 over x. But the moral of the story is that when we're taking the derivative of a constant, it becomes 0. But you wouldn't write it when you're taking the derivative normally, but I'm just going to write it anyway. So the idea is if you're taking the derivative of a constant, it's 0. And that's our final answer. That would be our derivative right there. So we only had to use the power rule in this example. And in a few other examples, I'll explain how to use the other rules. And Yeah, I'll show you how to do one with the chain. I'll show you the chain rule right now, actually. So let's say we're taking that y is equal to x plus 1 squared. We want to take the derivative of this. So dy dx is equal to, we use the power rule, 2 minus 1, and then that becomes, that 2 comes out the front, so that's why that 2 is here, yeah? So it's 2x plus 1. Now we take the derivative of x plus 1. Well, x to the power of 1, that's just going to be 1. And then the derivative of 1 is 0. So that's 2 times 1. Well, that's just going to be 2x plus 1. So the final answer is going to be 2x plus 2. And that would be our derivative. So this is what you would call the chain rule. So when you use the chain rule, you use the power rule, right? Just as I did here, 2, and then multiply by x plus 1. But then you take the derivative of what's on the inside. So it's what you would call also the outside-inside rule, because I did the derivative of the outside. I left the inside alone, and then I took the derivative of the inside. So that's why people call it the outside-inside rule, like outside-inside. But chain rule sounds way cooler, so that name kind of stuck. But outside-inside rule's still hanging around. It's chilling. It's, you know, doing its own thing. It's, I don't know, going on a holiday every now and then. But yeah, this is an introductory video to derivatives, and I'm going to show the other rules, like the product rule, the quotient rule. I may derive them, but I don't think so, because that's boring. Well, if you're not into math, it's boring. But yeah, catch you later.